Okay, well, welcome to everyone. And Glad many of you were able to join us here early for the second in our TMIP AI webinar series. This one is focused on machine learning in trip generation. Um, uh, in case the Zoom didn't let you know, to be clear, this is being recorded, um, and it will be available afterwards. We'll do another post on the Team Up listserv again, like we did after the first one, making it available there, and hopefully we'll also have a static link and be able to get it up on a website for you here shortly. Um, we are again, um, uh, uh, unfortunately for this one, we are again limited to 100 attendees. I think we are at that limit now. Um, but for next time, we will have increased capacity up to 500. So hopefully going forward, we won't have the capacity issues. But we are limited again here today. So, as I said, today is the second in our webinar series. If you missed the first, whether you weren't able to join us because of the capacity limits, or simply schedule conflicts or whatnot, the recording is available. There was a TMIP post um, here last week on that. If you're on the TMIP listserv, and as I said, if not, we're going to try to get all of them posted online. And when we do that, we'll do another listserv post about that. So, with us today, our presenters are Dr. Hadi Sadr with Iteris and Shi with NC State's ITRI Center, which is the agency that maintains the travel model for the North Carolina Research Triangle region, the two MPOs there for Raleigh and Durham and Chapel Hill and so forth. So excited to have both of you guys with us. Um, in addition to reminding everyone that this is being recorded, I want to go ahead and um, uh, show the official disclaimer that the views expressed in the webinar are those of the presenters and don't constitute an endorsement or recommendation or specification by Federal Highway. I think probably everyone who's familiar with TMIP knows that, but um, also just a reminder, in terms of the webinar series, this is the second in the series. The third will be next week at the same time. We'll be presenting on some of the destination choice work that has gone on as part of this Federal Highway project. I'll be presenting together with my colleague Andrew Roan. There are going to be several more webinars in the series, and we'll be announcing hopefully the next one or two, the dates for the next one or two next time. We are going to start to slow down the pace after the third one, so we'll probably just have maybe a couple webinars in July and a couple in August. But we do look forward to having several more really interesting topics. On a number of travel forecasting and modeling kind of items. So hope that you can join us for as many of these as you can. And again, we'll be trying to provide recordings and slides for those as well. Um, just to introduce today's webinar really is kind of focused on the practice more than the theory, and looking kind of at things that have already been incorporated, machine learning methods that have already been incorporated in adopted models that are in use by agencies around the country. In particular, we're going to focus on two methods. The first one that was incorporated almost 10 years ago, actually, in the Tennessee statewide model is that of boosting. And Hadi is going to be presenting on that. And then the second is the use of decision trees. And C is going to be presenting on that. So it's good to be aware, though, that these are not unique examples. Obviously, it's not standard practice at this point, but there's a growing number of agencies around the country that do have incorporated these new methods in their models. And so, um, I think this is good to be aware of. Some of the things that we're going to be talking about in this series, including in the next webinar next week, include some very advanced and complex methods. But some of the stuff that we're going to talk about today is actually relatively simple. So this, hopefully this will be a very accessible webinar for a lot of you. You'll be able to, follow in detail, and you may see applicability for, some of your work. So with that, I will go ahead and turn it over to Dr. Hadi. And if you want to share your slides and unmute.
Okay, can you hear me now?
Yes.
All right, great. So let me share my screen. Do you see my screen now?
Yes.
Okay, great, great. Um, Hello, everyone. Good afternoon and good morning to friends from West Coast. Um, my name is Hadi Saad, a senior manager at Iteris, and I would like to thank everyone for joining this webinar, and also thank Dr. Vince Bernardin for reaching out to me and suggesting to present this work. I really appreciate it. So today, I'm gonna talk about how we use boosting as a simple machine learning methodology to improve non-home-based models and to incorporate accessibility. And let me here acknowledge that this is based on the work that I completed at RSG between 2016 and 20 under Dr. Bernardin's supervision. So, okay, all right. So let's have a, overview of what we are going to talk about today. As some of you might know, TMIP introduced three different methodologies to model non-home-based trip. And those methodologies have become more and more common these days. On the other hand, we have boosting as a basic type of ensemble modeling and machine learning techniques that has been shown to be very effective. And because of that, it is also very common in data science. And because of that, we decided to use boosting in travel data models and see how we can actually use it to uh, increase the performance of the model, especially for non-home-based trip, and also to incorporate accessibility and sensitivity to accessibility. Uh, but what is the basic TMIP non-home-based methodology? I would call it basic TMIP non-home-based methodology for the purpose of this presentation only, because later on, I will explain how we add boosting to this methodology. So in 2018, TMIP published a new report with three different methodologies to model non-home-based trips. And those methodologies, they have been used in different areas in like over half a dozen statewide models, in more than 20 MPO models, in more than 10 states. And currently Tennessee and Florida DOTs are including this methodology as part of their standard modeling guidelines. But what are the issues with the traditional non-home-based methodology? So let's go over, a little bit of history of non-home-based trip and see, where they were added to the model. So back in 50s and 60s, non-home-based trip were added to the model, and the purpose was to increase model volumes on the network to match up the counts. And back then, the share of non-home-based trips among the whole trips, daily trips, was about 15%. But nowadays, based on the most recent surveys that we have, we noticed that we have at least 30 to 35% of daily activities as like non-home-based trips. So there is a significant change in travel behavior, especially for non-home-based trip, and we see a lot more of this type of trip. Um, and by definition, non-home-based trip is disconnected from the household and also from all other home-based trips that are generated by the same household. And this disconnection impact on you know other dimensions of the travel like mode or time. I will talk about it later. So based on all of these issues, uh, we added non-home based trip to just pump up trips to match counts, but they over time they became like node to the model and they add to the complexity of the model. There are also two major issues with the traditional methodology of non-home-based trips that, they are more serious. The first one is physically impossible pattern for non-home-based trip, meaning that vehicles or trips disappear at point A and then appear again at point B without having any trip from point A to point B. And the reason here is that, in the tree-based models, we don't consider the concept of tours, and we just focus on legs on each tour, which are trips, right? So for home-based trips, we are okay because one end of home-based trips is always home and everything is starting or ending at home. But for non-home based trips, we don't have that kind of situation and they can start and end everywhere. And by this kind of looking at only trips or legs on each tour without having the connection between them or sequence of them, we don't know that home-based trip, which is the main or major source of non-home-based trip, starts from where and ends at where. So that's the main reason that when we look at the non-home based model, the traditional methodology, which is mainly based on land use, it's like vehicles or trips disappear and appear on the network. And another issue with the traditional methodology, with the old methodology, is that they respond to new development unreasonably. Uh, I can explain this situation with these, networks. So imagine that we have a new residential development in a TZ or in small area, on the model network, and the network on the left is showing the new home-based work attracted to each zone because of the new development. So we have the model with and without development, and we have, home-based work attraction at each zone. So the gap between them, the difference between them is showing the impact of the new development. So the new home-based work attracted at each zone because of the new development. And look at the network on the right side. So this is the reaction or response of non-home-based trip, the traditional methodology. So this network shows the new non-home-based work trips generated at its own, right? And if you compare these two networks, right and left side, you see that there's a significant discrepancy between them. Um, for instance, let's focus on TAZs inside the red circle. So we have TAZs here that based on the network on the left side, we have zero or very minimal new home-based work attraction to those zones. However, the model is generating a significant amount of new non-home-based work trips in those zones. But let's look at the network in the middle, which is showing the performance of the new methodology. And you see that it is more consistent with the home-based work attracted to the zone, because in the new methodology that I will explain later, we are linking non-home-based trips to home-based trips attracted to each zone. So that is the reason you see more compatible patterns between non-home based trips generated at the zone and home-based trips attracted to those zones. We have that kind of, issues with other aspects of the travel, like mode and time. And let's talk about mode, for instance. So non-home-based trip are not conditional on home-based trip by mode. Let me explain through an example. If we have transit improvements in our network, so when we have that kind of situation, we see shifting from home-based and non-home-based trips to transit. So that is completely normal. And because of that, we see decrease in home-based and non-home-based walk trips. But in reality, when you have transit improvements, you will see more non-home-based walk trips, because in reality, we will have some sort of shifting from home-based auto to home-based transit, and those passengers that go to work by transit, they go to do their non-home-based trips afterwards by walk. So that is something that you can see in reality on the surveys, but the ultra and traditional methodology is not able to capture. So with that, let me um, talk about the basic TMIP methodology. So again, I call it basic because we later on we added the concept of boosting to this model. So in this methodology, we link non-home-based trips to home-based trips. In fact, non-home-based trip is a function of home-based trips attracted to its zone. And with that, we have to have some sort of significant change in the model structure. In the flow chart on the bottom left of this slide, this is the way of the typical trip-based model is working with the traditional non-home-based model. So we have trip generation, trip distribution, and mode choice in series, and within each step, we have all purposes in parallel, including non-home-based. However, in the new methodology, we have trip generation, which is shown on the right, bottom right flow chart. We have trip generation, distribution, and mode choice for home-based trips first, and then the outputs of these steps become input for non-home-based model, for non-home-based generation and then distribution. So the big and major change here is that non-home-based model is run in series rather than parallel with home-based purposes. And the home-based component of the model remains unchanged. It's exactly the same as the old methodology. However, the only major difference here is that the outputs become inputs for non-home base, and non-home base is run after we finish home base part of the model. This is the same actually flowchart, just bigger to make it clear. And another big change in the new methodology is that we estimate the trip generation for non-home based trips by mode. So there is no need to have a separate mode choice model only for non-home based trips. And coming up with the right values for coefficients and parameters in utility functions in mode choice is state of art. It is very difficult. It needs a lot of data. It cannot be based on the poor database. But with this methodology, trip generation and mode choice are combined, and we estimate trip generation by mode. So there is no need to have a mode choice model for non-home base. Again, another big plus for tree-based models. Okay, so that is, brief review about the uh, issues with the traditional methodology for non-home based and advantages of the new methodology for non-home based. Let's talk about boosting a little bit. So ensemble modeling has been one of the key insights in data science. And the whole idea here is that um, two models are better than one model. And when you have more than one model, you need to combine them. And you can combine these models either in parallel or in sequence. And boosting is a technique that is combining models in sequential way. Um, and we have a very general statement that we always say, which is all models are wrong, but different models are wrong in different ways. And um, by having different multiple models and combining them, it is likely and there's a chance that weaknesses of one model is compensated and covered by the strengths of the other model and vice versa. So this is the whole idea. We have more than one model and we are going to run them either in parallel or sequence. Here for the boosting situation, it is in the sequence way. And we try to just minimize the overall error, and each model is trying to fix the issues or errors of the previous model. So if we want to focus more on boosting now, the main idea of boosting, if I want to say it in a simple word, is that we try to fix the issue of the prior model. So first we estimate our model, right? The first model. So, or we train our first model. Then we identify the issues or errors of that model, um, which are called residuals. And then we try to train another model to fix the issues or, to minimize the residuals. And then we go back to the second one to identify now the new challenges, the new errors, and do that loop again to come up with the situation that, okay, so this is good enough and the error is within the reasonable range. Um, Boosting, just looking at the history a little bit. So back to late 80s, Robert Shapiro introduced this concept and proved it mathematically that when you have a series of weak models, they can boost each other to create a strong model at the end. So that was the major stone to build all of these, knowledge and skills around boosting. And in 1995, we have ATA boost, which is one of the earliest type of boosting, focusing on reweighting observations that we have some issues in the next, we reweighted those observations in the next models. So then next models will put more emphasis and attention to those samples with highest error. In 2001, we have gradient boosting. So in this methodology, instead of reweighting, we use residuals of the prior model in an optimization framework. And later on, in 2016 and 17, we have more advanced, fast, and efficient boosting methodologies like XGBoost, LightGBOM, or CADBoost. So they are more advanced and effective techniques to, boosting techniques. And some of them they are working with tree-based, some of them are not. So they are, more advanced boosting techniques. Okay, now let's talk about how we implemented boosting in our non-home based trips. So as I said, this is like a sequence of procedures. So in the first step, we estimate non-home based trip the way that TMIP proposed. So it is basic TMIP method. And as I explained earlier, we modeled non-home-based trip as a function of home-based trip attracted to the zone. So here, y hat is the non-home-based trip um, by mode M and type T, because you can have different types of non-home-based on work tour, non-home-based on other tour. And X is home-based trip attracted to the zone, again by mode M and type T. It can be home-based work, home-based other, home-based shopping. All of these home-based trips, are potential variables for this equation, and betas are parameters. So very simple, just a linear regression that you can come up with the values for beta. And with this, see, we are linking non-home-based trip to home-based trip. And because of that, we won't see the situation of appearing and disappearing trips in the middle of the tour, because now we are like linking them together. Um, all right, so this is the first step. So with that, we have the estimated non-home-based trip based on home-based trips. And then we added the concept of boosting to this model. And the whole idea here was that if you have a home-based trip to an area with a high accessibility, it is very likely to produce or generate more non-home-based trips. Imagine that you have two cases, one home-based work trip to downtown, and another one is like um, another home-based work trip to rural or suburban areas, right? So in the first case, we know that downtown areas, they have the highest accessibility in the region, with a lot of destination nearby, and opportunity to get to those destinations. So it is more likely for that person to go out for lunch in the middle of the work, or to go to the bank, or to go to do some sort of shopping after the work. So it is very likely or more likely to produce non-home based trip compared to the other case that is distinct at suburban areas with much lower accessibility. So that's the whole idea, that we wanted to add accessibility to the model. So now Y, which is the total non-home based trip, is A, which is the accessibility, and you can define different types of accessibility per your preference, like general accessibility, nearby accessibility. You have come up with different types of accessibility here, times uh, this term. And this term is exactly the same as the one that we estimated in the first step, right? So this one means that we are using accessibility as a factor to scale up or down whatever we estimated in the first step, right? So uh, alpha and gamma are the parameters. Now, um, you may say that this is non-linear formula, and it's not that easy to estimate the parameters. However, if you take log from both sides of the equation and take this term to the other side, you come up with this equation. Now you have linear form. On the left side, you have the residual of the first model when you estimated the model only based on home-based trips, right? This is the observed minus this estimated non-home-based trip in the first step. So that's the residual of the model. And then you have accessibility as a variable, and then alpha and gamma are parameters. So again, another linear form that you can easily estimate parameters. Uh, this actually, graph shows the impact of accessibility on non-home-based trips actually over time. So the curves on the left side shows, the form of impact that we actually thought in the beginning when we started working on this. At that time, we were more cautious and conservative, meaning that we didn't want to have the impact of accessibility on non-home base more than 20%. So within plus minus 20%. But later on, by looking at what implementation of this methodology in other areas, looking at different areas, we realized that nope, you don't have to be very conservative. Sometimes, this accessibility you know, can apply more aggressively. And, we come up with kind of something like that. Depends on the area. Again, this is not something that, you always have this situation, but it is also very common to have like 50% plus or minus 50% impact of accessibility on non-home-based trip, estimated from home-based trips. Uh, Now let's look at just, one example. This is the work that we did at Hampton Roads in Virginia, and let me, here acknowledge that, we reached out to Virginia Department of Transportation, Office of Modeling and Planning, and special thanks to Pong, who cooperated with us and provided us the documents of the work that we had done when we were at RSG. So all of these slides are based on that. So Hampton Roads is a very large area in Virginia. It covers Norfolk, Virginia Beach, super large area with about 1.8 million population, about 600,000 households, um, decent transit system. So it's pretty large and a busy area. We implemented this methodology, and the top box is showing the first step of the model estimation. We connected non-home-based trip by mode with home-based different types of home-based trips, home-based work, home-based other, again by mode, SOV, HOV, and even transit, because it is very common that you drive, right? You go to your work by auto and then take a transit later to go somewhere else inside, in downtown area, for example, because of lack of the parking spots or anything. You prefer to take a transit. So it's very common that the home-based trip mode is different, but they are conditionals, and that is the reason that we, by having this type of equation, we make a correlation between home-based trips attracted to the zone by mode and non-home-based trips generated at that zone by modes. Then the middle box is showing the general accessibility that we defined, which is a function of home-based other attraction again, and also travel time between this particular zone and all other zones. We came up with this definition as a base approach to define accessibility, and then the bottom box is showing the final product. This is scaled non-home based, the final number of trips as a function of accessibility and also home-based trip. And just two more slides for the results of the model and comparing it with the survey. So the top table is showing the trip generation results. Let's look at these two rows. We have non-home based on work tour and other tours. Based on the survey, for instance, for non-home based work tour, we have one trip per household, and the model was able to generate 0.97 trips per household. And for the other type of non-home base, we have 1.79 versus 1.77, so pretty close. And here, just take a look that, um, based on the survey, we have 2.79 non-home based trips per household out of 8.75 daily trips. So again, it is about 31% of daily activities. As I said, nowadays we have between 30 to 35% of daily trips as non-home based trips. And the bottom table is the mode choice results. Again, you can see percentage of trips by mode, peak and off-peak model versus National Household Travel Survey for that region, which are pretty close. And also this is the distribution, trip length frequency distribution for non-home-based model, peak and off-peak, which, the model performs well, and it was able to replicate whatever happens in reality. So if I want to conclude, say that this is one attempt to use a new data science technique. Here is boosting intra-model modeling, and especially machine learning technique. And when we talk about machine learning or AI, that kind of things, these are very scary terms. But I wanted to show that, although they seem scary, but sometimes you are able to just simplify them and use it to enhance your model, like what we did here. And the enhanced model performs better than the original non-home-based model. It is sensitive to accessibility, and we were able to implement this concept that if we have a home-based trip to an area with high accessibility or close to a lot of destinations, with a lot of destinations nearby, it is very likely to generate more non-home based trip. And by this approach, we were able to implement that. So with that, I would like to hear your comments, and if you have any questions, um, feel free to ask. I will be more than happy to answer your questions.
Yeah, I think we'll do questions at the end.
Okay.
And that way maybe we can get discussion, a little bit, and both you and C can kind of chime in. Although, um, please feel free to use the chat as well. To if you have questions, I see at least one in there. And there, could be a reply there as well. But thank you, Hadi. Appreciate your sharing all that. Again, I think this is a straightforward kind of application of one of the key, methods of machine learning. And so that's hopefully something that folks can kind of immediately see, its relevance for the kinds of things that they might be doing. So, again, thank you, Hadi. Please stick around for the questions at the end. But let's turn and I'll introduce Si Shi, who leads the development and maintenance of the Triangle Regional Model for the North Carolina Research Triangle area. That's the Raleigh, Durham, Chapel Hill region, for those of you who might not be familiar. And she is going to share about some of the machine learning methods that are incorporated in their model, and especially decision trees, as that was the first model to incorporate those. So, see, are you there? You want to share your slides and say hello?
Yes. Hello, everyone. Let me know if if you can see my slide or not.
Yep, now I can.
Awesome. Oh, and also one side note, I just realized we have a drill test going on, so hopefully the alarm won't go on during my presentation. So, okay, good luck. Good afternoon,
Fingers
everyone.
crossed.
Yes, fingers crossed. Good afternoon, everyone. My name is Sishi, and from the Institute for Transportation Research and Education. I'm happy to be here to talk about how machine learning was incorporated into the Triangle Regional Model Generation 2, or we call TRMG2. The focus of this presentation will be on trip generation and the non-home-based model. Before jumping into the technical details, let me first provide some context about the triangle region and the model itself. So the TRMG2, the triangle region covers Raleigh, Durham, Chapel Hill, Cary, Wake Forest, and many other growing communities. There are two MPOs, and they're sharing just one model. So none of them are having this model, but we are the custodian. Unlike many other metropolitan areas that have a single dominant urban core, the triangle region is very multi-nucleated. Travel patterns occur between many different activity centers rather than simply going into and out of one area. The region is home to three major universities, including UNC Chapel Hill, Duke, and NC State. It has nearly 2 million residents. And now a brief overview of the TRMG2. On the right, I'm showing the flowchart of our model. So once you open the interface, this is what you see. It's a hybrid trip-based model, and Caliper delivered it to us in early 2022. At that time, I know very little about AI, and ChatGPT, I don't think it become a household known name at that time. And I certainly wasn't thinking about how AI could be applied to travel demand modeling. Our model represents approximately 800,000 households, and it covers 3,500 square miles and 2,900 TASs. And one good thing about the G2 model is that it's live on GitHub. Is completely open source and maintained and on GitHub, allowing transparent development and peer review. So I put a QR code here. So if you are interested, feel free to check it out online. And so what makes it different from the previous triangle regional model? So first thing, trip making is sensitive to characteristics such as age and neighborhood type, not just household size and income. And also this model includes a all-street network, which better represents walk and bike. It better captures travel among multiple activity centers throughout the region. And we also added newer travel options such as ride hauling and borrowed vehicle modes. We also have a non-home base model that links trip mode to the home base trips, making travel behavior more realistic. There is also an explicit parking model that handles parking behavior near downtown and major university area where parking is highly restricted. That brings us to the overall model structure. It's disaggregate all the way until the mode choice and destination choice. At the very beginning, we have a population synthesizer that generates household and person profile for the entire region. And then we get into the home-based trip generation, still generating trips, but trips are segmented by tour type. And next, we will split those trips into motorized and non-motorized trips, and then only the motorized trips will flow into subsequent steps. There are many advanced components of the model for G2. It uses machine learning methods in trip generation and the non-home based model. It also have nested destination choice model. So let's talk about how we select the machine learning methods that were used in TRMG2. We tested a wide range of approaches, including traditional cross-classification methods, generalized linear models, ordered logic, and more advanced machine learning approach such as XGBoost. Using the K-12 trips as an example, the chart on the right, you can tell that XGBoost achieved the highest statistical fit. However, the fit alone was not our primary objective. Our goal was to identify a relationship that was explainable, behaviorally reasonable, and stable enough to be used in a long-range transportation planning model. That is why we ended up with decision trees. It provides the best balance between predictive power and interpretability. So what is decision trees? It's a game of 20 questions. The chart on the right shows a decision tree for home-based tour, home-based work trips on a work tour. The variables that appear near the root of the tree are generally the most influential variables in explaining the behavior. Not surprisingly, the first two things that stands out is worker status and age. Think about if you are going to predict work trips, then the first question you are asked is whether you are a worker or not. And also we see the presence of children, senior, and another worker in the household also appear as important explanatory variables. These variables interact with each other in ways that would be difficult to represent using a traditional cross-classification structure. The next one I'm showing is home-based OME trip. This trip purposes capture shopping, dining, and maintenance activities. For those activities, age emerges as the most important indicator, which you can see on the top of the tree. Accessibility also appears prominently, indicating that people in more accessible environment, they'll be generally making more trips compared to those are not. Employment status become another important variable as well. And this next one is showing other discretionary trips with long duration, which are activity duration longer than 30 minutes. Similarly, the tree identifies the worker status, age, accessibility, the whether you are a child or not, and also your personal income as the major explanatory variables. So this one is for the non-work tour, home-based, other discretionary trips with short duration, less than 30 minutes. These are trip activities less than 30 minutes. Think about like if you go to the post office to drop off a package, trips like that. And for this one, the household composition become especially important. Like whether you have keys appear at the top, and also the presence of children, senior influence trip rates substantially. Accessibility again appears as a key explanatory variables along with your age. As you can see, decision trees provide a natural way to uncover this non-linear interactions without requiring us to specify them in advance. Traditional trip generation model often focus primarily on household size, vehicle ownership, or your income. But in our example shown above, age and accessibility also appear consistently across many trip purposes as powerful variables for differentiating trip-making behavior. So this provides evidence that demographic characteristic and neighborhood context play a larger role than many traditional trip generation approaches assume. And now we're jumping into the non-home-based trip generation model. A key behavioral insight here is that every path leading to a non-home-based SOV trip begins with an earlier home-based trip made by auto. In other words, you need to have a vehicle available with you in order to make a subsequent SOV trip away from home. So this creates a strong behavioral linkage between the home-based model and the non-home-based trips that is often missing from the traditional trip-based model. And this is for the non-home-based walk trips. And for this one, many more pathways become possible. Unlike auto trips, walking does not require you carrying a vehicle with you. So as a result, a variety of earlier home-based modes can now lead to a subsequent non-home-based walking trips. One interesting observation is that auto pay modes often generate subsequent walk trips more because people they just get off the car and then continue their traveling on foot. This demonstrates how subsequent non-home-based trips interact with the previous home-based trip portion. You've seen this in Hadi's presentation earlier. Again, we also use this boosting method to improve the non-home-based trip generation. The TRMG2, we model the non-home-based trips as a function of both home-based trips and accessibility. Accessibility acts as a scaling factor that modifies the production of home-based trips. This allows areas with different level of accessibility to generate different amount of non-home-based travel, even when the home-based travel levels are similar. This approach creates a more realistic representation of the non-home-based travel pattern. Now, the last slide, it shows how accessibility influences non-home-based trip generation produced by this formula. As you can tell, as the accessibility increases, the non-home-based trip production rate increase. Notice that the especially strong effect for non-motorized trips, for walking trips, generation approach zero in areas that are not walkable at all, while increasing significantly in highly accessible areas. So this highlights the value highlights the value of incorporating accessibility directly into home-based trip generation. And I'll be happy to take any questions.
Thank you, C. Yeah, so I think you can see how in the triangle regional model it implements both of these methods, both the boosting of the non-home based trip generation, but also introduced decision trees for trip generation as well. With that, we do have some time for some questions and answer. Uh, for the first webinar, we simply used the chat. I think, we can continue to do that. And although Sarah too, if I don't know if you want to um, unmute people who raise their hands if people want to ask questions as well. Um, uh, we'll start with the chat. I tried to respond a little bit, to a great question about why not, incorporate accessibility, directly kind of in the original linear model. And the reason there is that that we don't want to break the necessary connection between the home-based trips and the non-home-based trips. And so uh, the and really the boosting approach allows us to create a really nice nonlinear model simply as a sequence of two linear models. So it's really it's kind of part of what's nice about that approach. Um, and someone also asked about how boosting could be applicable in activity-based models. And this is a very general, boosting is a very general kind of method. And so it absolutely could be incorporated there. The component models of an activity-based model, of course, are generally logit discrete choice models. Those also can be boosted. There's certainly academic literature about boosting logit models. I'm not aware of anybody who has boosted logit models in an ABM in practice. I'd be really thrilled and interested to learn if anybody has. Yeah, so that was just a couple responding to the questions in the chat. Hadi or C, do you want to chime in or add anything on either of those questions? Or I think maybe we've got one or two more that
Yeah,
have come in since.
yeah, no, you just explained that about the first question. Definitely adding accessibility as a separate variable, what happens is that, we may lose the connection between home-based and non-home-based trip. In fact, that, in an area with a very high accessibility, but nothing else, so there is no such a home-based trip there, but, you know, accessibility by itself as a variable can, produce trips. Again, we are losing the connection between home-based and non-home-based trips. So that which is you know, the main idea of the first approach, the first step of the model. So because of that, accessibility is like a factor or a scale, um, bringing up or down the estimated trips in the first step. That's the role of accessibility. And regarding the second one, yeah, you also mentioned that. I think that it can be used in the destination choice part to uh, give more weights or uh, lower weights to some zones when the model is uh, selecting zones for each trip. Uh, in fact, we are just talking about the boosting. The first part of my presentation, which was about the TMIP methodology, it doesn't have, it's meaningless for activity-based models because, that is purely based on tours. We are I just talked about the boosting techniques. Yeah.
Yeah, great. Um, there was a question about comparing and contrasting nested logit models with decision trees, and I think it's kind of a very intuitive, natural question because they both obviously use kind of tree-based structures, right? We call them, of course, nests in the choice models, um, but those models and those methods are actually very different. The nested logit models remain really continuous, fundamentally continuous models, whereas decision trees are highly discontinuous, uh, um, and so those are actually very different methods, and in the context, going back to the context of boosting, it potentially can make them very complementary, but yeah. Um, uh, there's another question.
About the log
About
transformation.
how decision trees were
Oh, decision.
used. Um, and so see, I guess obviously you had a few slides. I don't know if you want to go back and show some of those to help answer that, or um,
Sure. I can pull the home-based work trips as an example.
yeah.
Um, yeah, so the decision trees is used in our home-based trip generation model. It's basically used to determine your trip rates based on your personal characteristics and the built environment near you. So for instance, like if you are a worker and then you go some, if you're not worker, then you go down this tree, and if you are not, then you go down the other. And it also look if you're not a worker, then like are you a teenager or are you senior? Do you have other kids in your household? Do you have other workers in the household? Based on your different answers, then you arrived at different trip rates. And those trip rates are applied to our person table to generate trips, and then those trips will be aggregated to TAC level and then flow into our subsequent model steps.
Mhm. Yeah, so this is a hybrid trip-based model as C was showing, and so it does start with a synthetic population. So there are, as she was saying, there's a table of individual persons that's generated, and this is applied to that. And since these are home-based trips, you can, if you want, equivalently, this is really like tour generation, right? Because
Mhm.
every tour for every tour, there's two home-based trips, and so so this is kind of at that stage of the activity generation or trip generation, tour generation, however you want to cast it, and yeah, and those relationships, the trees were developed, were estimated using the local survey data.
Yes. Oh, yeah. The number inside the bubble is the trip rate. Yes, you're right.
And regarding the question about the transformation, why did we use the log transformation? So the whole idea here is to make it in a linear format and also, um, making like a residual on one side. Um, then it would be, it makes it very easy for the second model estimation. But any other transformation that makes it easy and, simple to estimate the parameters is also, you know, it's okay. There is no, uh, restriction on we have to use only the log format.
Yeah, no, I think yeah, Hadi, that's right, and you absolutely could consider other transformations. I think you do want to, in addition, and I think convenience is a factor. I think we do want to think about the behavioral, kind of implication of the transformation as well. And in this case, I think the log makes a lot of sense in terms of, if you look at those curves that both Hadi and C showed, showing kind of the way in which accessibilities modify the trip rates. I think that it can produce a range of curves, and all the ones that we've seen, I think, make sense. Let's see. Other questions. Someone asked if we could elaborate how the accessibility is evaluated. So, oh, okay. So, um, I can answer that, but how do you see? Do either of you guys want to jump in there? I think you're
Sure.
both pretty familiar with the accessibility variables, how they're calculated in these models.
Yeah. So again, let me share my screen. Maybe I can. Right. Do you see my screen?
Yes, seeing it now.
Yep.
Okay. So again, there is no um like a specific type of definition for accessibility. You can use um, any variable um, to come up with some sort of accessible definition. But for instance, for this project, the way that we define it is like for zone I, we looked at home-based other attractions at all other zones times the exponential of travel time from those zones to this particular zone that we are calculating the general accessibility. So in fact, we are looking at the how difficult and how hard it is to get to this zone, right? And also what are the about the availability and the options for the other zones to get to this point. So um, this is the general accessibility. We have other types of accessibility like nearby accessibility, um, or other types. I don't remember names at this point. But again, you can, you know, define it based on other variables. You can use land use variables if you want. There is no such restrictions that, okay, so you have to use um, home-based trips, home-based other trips. But we looked at, okay, home-based other trips is a good indicator of, you know, the activities that are happening in that zone, and we defined it in this way. Vince and she, feel free to add anything that you know that you think that you need to add.
Yeah, thank you. No, yeah, and yeah, I forgot you actually have an equation for the one you used there for Hampton Roads. Yeah, these in these models, these accessibilities are generally gravity log sums, which are easy to calculate, and with accessibilities, there's kind of several different things that can vary, right? One is the attractions that they're measuring accessibility to. Another is kind of the distance decay, the form of distance decay, and then the mode of the travel times used in that distance decay. Um, all of those are kind of key things. And in these models, several different accessibility variables were used. Um, uh, and some of them were, a little bit ad hoc, like that Hampton Roads one. Others were a little bit more formalized. I think the ones in the triangle regional model used gravity log sums that were based on combinations of the simple generation and gravity models in the old NC-Chirpy 355. And so there were some that measured kind of accessibility to all attractions based on kind of distance decay for all trip lengths. And then there are others that were a little bit more focused on like the trip lengths, a sharper distance decay, more related to like non-home based trip lengths. and so forth. So, um, but obviously there are many ways to calculate accessibility and yeah. Ah, and then a good question from Jujan about age. Since age is used in the decision trees, is there a separate aging population model applied to future years, or is the age only taken from the base year PUMs? Given that the retirement age and average population age keep increasing, it would make sense that the age cutoffs might need to shift for future years. Oh, from Rebecca, not Jujan. So yeah. Um, right. Obviously, that is part of the whole idea of why it's a good thing to have age in these models is because of the aging population, which is an issue in general in the country, some places more so than others, though. In terms of there is a separate synthetic population for the future year scenarios in the triangle regional model. In terms of the development of the control variables for the future years, that I don't remember off the top of my head. See, can you speak to that?
Yeah, sure. So I believe the control is the same for base year as well as the future year. But right now we have an active investigation going on considering changing the future age distribution for the next generation model. But still underway. But right now it is the same for base year and future.
Okay, yeah. So yeah, so hopefully that'll be something interesting for you to kind of look at as you're able to incorporate that new kind of aging population in some new future scenarios. But
Mhm.
the behavioral sensitivity is there in the model to support that. So yeah. Well, these are some great questions. I see another one just popped up. Um, and I think we can, probably take one or two more, but and obviously we're fine on time, but at the same time, want to be mindful of people's time. And so, if anybody does have a last question or two, please feel free to chat it in. But probably, in a few minutes, we'll probably go ahead and wrap this one up for today. Um, uh, and so this one is about what other variables undergo shifts in equation values across different versions of the original model. Um, I'm not sure if I know exactly what that's asking. Hadi or C, is that clear? Are either you clear on exactly what that's asking?
No, now I'm thinking um, the original model. I mean, the first step, or
Yeah, I'm not sure if that question is
uh,
about the boosting of the non-obeyed trips or about decision trees. Uh, if you want to, Alexander, if you want to follow up to clarify, okay, about decision
decision
trees.
tree.
Um, oh, well, there are, I think, see, I think you did a nice job of pointing out the sensitivity of the decision trees to a bunch of different variables. There were a bunch of different variables that did that showed trip rates varied significantly with I don't know, see if you want to elaborate or add specifics or
Um, I because E-tree is not involved in developing the decision tree, but I would imagine all of the variables available both in the population synthesized files as well as the SE data table. Everything is included in the original model. And those who determine to be the most influential are picked in the decision tree, which is what we just showed earlier.
yeah, thank you. And there's a follow-up. Yeah, this might be about the future year synthetic population.
Ah,
So yeah, I don't know if you're looking at other variables in addition to age for, that you might consider varying for different scenarios with that.
yeah, we're considering age as well as the percent senior, the percent child, as well as the income. But income might be less priority because it's a bit tricky to predict in the future. So yeah, right now the focus is only on the age distribution.
Great. And then there's a question, do the non-home-based trips keep track of walking trips? And
Yeah, yeah, so we can consider non-motorized trips as one of the modes. As I said, we have non-home-based trip generation by mode. So it depends on the sample size and how strong and reliable is your survey for the model estimation. But if you have a good uh, sample size regarding non-motorized trips, definitely you can have it as one option, and then split between walk and bike, probably based on some factors.
yeah. Yeah, and I know that yes, like for instance, in the triangle and some other models, walk trips are carried forward or and calculated separately at the non-home based level as well. Um, all right. Well, thank you to everyone for joining us today. I think obviously um, uh, this is, a little bit some of the simpler kind of methods methodologically, that we're going to be looking at in this series. And so, didn't require quite as much time as some of our other topics might. But I want to really thank both Hadi and C for sharing their excellent presentations on these real world examples of travel models incorporating machine learning methods. Um, Thank you again, Hadi and C. We really appreciate your being part of the series. Look forward to more presenters addressing a whole host of things over the course of the series. Hope that many of you can join us again going forward. But with that, I think we'll go ahead and wrap things up for today. Thank you very much.
Thanks, Biggs.
Thank
Thank you,
you.
everyone.